Well, the chemical equation gives us the relationships in terms of moles. But practically, we are interested in the relationships in grams, because we can't measure things in moles, but we can measure things on a balance using grams. So here's kind of the big idea of what's going to happen here. If we have a mass of one substance, and we want to know the mass of another substance. Maybe we have mass of oxygen, we want to know mass of water. We need to go through moles. So we're going to take that mass of A and use its molar mass to convert it into moles of A. We did this before in chapter 6, I think. Calculating a molar mass and converting between grams and moles. Then we take moles of A and go to moles of B. That's what I just finished teaching you, using the mole ratios from the balanced chemical equation. And then we take the moles of B and we convert it to mass using the molar mass of B. So we're going to take one old skill and one new skill, and we're just going to put them together. So here's an equation. This is octane. Octane is one of the components in gasoline. And when it combusts, do you recognize this as a combustion reaction? Reacting with oxygen, forming carbon dioxide and water. 2 moles of this will give off 16 moles of carbon dioxide. But the question is, what mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2, 500 grams of pure octane is burned? Well, this is also dimensional analysis. What is the number? We've got 5.0 times 10 to the 2 grams of octane. So grams. Now, we didn't give you the formula for octane, but you should be able to figure out which one it is by process of elimination. You should know that this is oxygen, that's carbon dioxide, and that's water, so this guy must be the octane. So that's what we're given. We're given grams of octane, C8H18. And they want us to find mass of carbon dioxide. I find that the balanced chemical equation is a very helpful thing to organize the information. So here I've got an amount of octane. So under the formula for octane, I'm going to write that. 5.0 times 10 to the 2 grams. And the question is, how many, question mark, grams of CO2? The path that we use in stoichiometry is always the same. Grams to moles to moles to grams. And you just kind of have to chant that for a while. It's a little bit like the group 1A, 2A, 3A, zinc or silver. You say it enough times and then you just remember it. If you wake up in the middle of the night muttering grams to moles to moles to grams, you know you've been studying enough. Okay? Grams to moles to grams. So our path here, we're starting with grams of octane. We're going to go to moles of octane. From moles of octane, we're going to go to moles of carbon dioxide, and then to grams of carbon dioxide. Grams to moles to moles to grams. Grams to moles to grams. Grams of octane, because that's what they gave us the mass of. At the end, grams of carbon dioxide, because that's what they asked us to find. We go from grams of octane to moles of octane because we only want to change one thing at a time. Here we're not changing the compound, we're just changing the unit from grams to moles. And then from moles of octane to moles of CO2, we can do that using the coefficients up here. Again, we're only changing one thing. Now the unit is the same, but the substance is different. The compound is different. And then moles of CO2 to grams of CO2, again changing one thing, We're changing the unit, moles, to grams. We're not changing the CO2. Any questions about the path? Grams of the first thing to moles of the first thing, to moles of the second thing to grams of the second thing. Once we have this path laid out, it should all just fall into place. I have 5.0 times 10 to the 2 grams. It's important to write grams of what? Grams of octane. C8H18. I've got 3 arrows. I'm going to have 3 conversion factors. Grams octane to moles CO2 to grams CO2. Those are the things that go on this line. So here's moles octane and moles of CO2 and grams of CO2. I'm going to take this unit and put it in the denominator because that's the unit I want to go away. I want it to cancel out. And then I'm going to put moles of C8H18 down here. So those cancel out. And moles of CO2 down here. You don't have to worry about remembering, should I multiply or divide by the molar mass? Which moles goes on top and which on bottom? You set it up like this and the unit tells you what to do. Now we need some numbers to go in here. I think the middle one is the easiest. It's nice to start with something easy and you kind of build a little confidence. So mole to mole ratio comes from the balanced chemical equation. So here we have CO2. We find CO2 in the equation. It's got a 16 in front of it. So I'm going to write 16 in front of moles of CO2. Octane has a 2 in front of it, so I'm going to put 2 in front of octane down there. You could simplify that. I wouldn't. You're going to be using your calculator anyway. Sometimes when you simplify stuff like that, you goof up, and that's a sad way to get a problem wrong. If you're going to get it wrong, just really get it wrong. How do we find grams of octane to moles of octane? Molar mass. And we're just going to have to calculate that. We've got a periodic table, we've got a calculator, and we've got the formula. So for C8H18, there are 8 carbons, 12.01, and there's 18 hydrogens, 1.008. 8 times 12.01 plus 18 times 1.008, 114.224 is what my calculator gives me. And that would be grams of octane per mole of octane. That should have 4 significant figures. I'm going to let the 2 and the 4 trail along. They're not going to hurt anything. So 114.224. And then we need the molar mass for CO2. So for CO2, 12.01 plus 2 times 16. That equals 44.01 grams per mole. Bless you. Any questions? We've done this step before, and we've used this before. We're now just putting them all together. Did I screw something up?
Is there just one mole of octane for the first one?
Oh, here? That's a very good question. Is there just 1 mole here? Because it says 2 up here. Excellent question. And that is a very common mistake students make. The 2 is addressed here in the mole ratio. What we're using here is the mass of 1 mole. Okay? It's the molar mass, it's the mass of only 1 mole. If we wanted to put a 2 here, we'd have to multiply the bottom by 2 also, and that just makes things difficult. And so we're not going to have a 16 over here. We want the mass of 1 mole of carbon dioxide. Does that make sense? Okay, good question. So 5 EE2 divided by 114.224 times 16 divided by 2 times 44.01. 4 didn't go. 44.01 equals. And my calculator is giving me a big long mess that I don't have room to write. Stick it up here. 1541.182238. Did you get something like that? Anybody? Yeah, okay. Little tiny nod in the back row. Thank you. Well, what do we do with sig figs? These are not exact, but this has 4 and that has 4. These are exact. How many sig figs in my starting number? Just 2. I'll give you a shortcut here, a hack, if you will, if you are having trouble with significant figures. In stoichiometry problems, it's usually this starting number that limits the number of significant figures. So you can kind of just use all of them for the rest of it and you'll be fine. If this has 2, just round your answer to 2. So that means I want to round it to the 5. Now this is where I've seen some stuff that I understand why you do it, but it is also extremely silly. I'm getting a lot of things in lab reports where people round that number to 15. Okay, rounding the number to 2 significant figures does not mean you just get rid of everything else. Okay, so we're rounding to this place. This place is the hundreds. So rounding 1,541 point blah, blah, blah to the nearest 100, what would that be? 1,500, right? It's better to put it in scientific notation, but people are having trouble with that too. So I want to just think about this. Okay, when my daughter was in, I think, 3rd grade, they were rounding to the nearest 100 place. They were rounding to the nearest thousands, rounding to the nearest 10. I know you all have done that. Now maybe you forgot how. If we're rounding to this place, I'm going to look at this digit to see, do I round up or down? But then I can't just chop everything off. Because I could make a lot of money in business that way. Oh, you want $1,541 for your used car. Let's just round that off and I'll give you $15 for it. Is that good? Would you go for that? No, you get it when it comes to money, right? You can't round $1,541 to $15. You just can't do it. You can't do it with grams of carbon dioxide either. So you can call this 1500 grams of CO2. That's okay. It's better to put it in scientific notation because these 2 zeros are technically ambiguous and they can be confusing. Okay, so quick review of scientific notation because I'm seeing issues with this as well. You're going to look at the decimal point and you're going to move it until it's after the first non-zero digit. So I'm going to do this in a different color. I'm going to move the decimal point 1, 2, 3. 1, 2, 3. This stuff doesn't matter. Don't count all of those. That doesn't matter. Some people are moving the decimal point over and then they're counting all of these. You know, you missed something. We need to get that fixed because that's going to continue to cause a problem. So we move the decimal point 3 places. Sorry, this is getting super messy. So that's going to give us 1.541 blah, blah, blah times 10 to the third grams. I haven't rounded yet. This is a positive exponent because 1,500 is a big number. You say, oh, well, that's not such a big number. Well, no, if you had to pay a traffic fine that was $1,500, you'd say that was a big number. Okay, it's bigger than 1. So this is a positive exponent. A couple of you still have that backwards. So positive exponent. Now, when I round it to that digit, I can just chop those digits off and call it. Let's do another example. What mass of octane would be needed to generate 42.3 grams of water? So we'll go through this one a little faster without all the commentary. Okay, so there's the question. You got to read the whole question. Find the numbers. 42.3 grams of water. I'm going to write that under water. 4.23 grams. What's the question? What mass of octane? Well, the unit we usually use is grams. So question mark, grams of octane. I'm given a mass, and I'm asked for a mass. I have to go through moles, though. Grams to moles to moles to grams. Grams to moles to moles, whoops, to grams. I didn't leave myself any space here. We're starting with grams of H2O. So I'm going to go to moles of H2O. I want to know about octane, so I'm going to go to 6. Where does 6 come from? C8H18, and then grams of C8H18. Grams of the first thing to moles of the first thing, to grams of the second thing to moles of the second thing. 4.23 grams of water. Yeah, it is 42. I'll just write the whole thing over again. 42.3. Okay. 3 arrows means 3 conversion factors. 1, 2, 3. The moles of water, moles of C8H18, grams of C8H18. I know that writing all this out gets a little tedious sometimes. Repeating the course because you flunked the exam on stoichiometry also gets a little tedious. We should cut it out of the class. Yeah, unfortunately we can't tailor the class to what's just convenient and easy. I am the teacher. But there's this thing called a course outline, and there's this thing called transferring to a 4-year college. And there's this thing called OChem, and if you have to take OChem and you don't know how to do this, you're going to be in trouble. So, no, when you're in OChem, you don't have time to learn anything but OChem. Okay, so the mole ratio, what do I put in front of the C8H18? 2. And what in front of the H2O? 18. Okay. We did the C8H18 already. That was 114. Was it 224? Grams per mole. And then water, 2 times 1.08 plus 16 is 18.02. So we've got 42.3 divided by 18.02 times 2 divided by 18 times 114.224. And I get this big old number, 29.7920. And there, it keeps going on, and I'm like, how many of these digits do I have to write down? Started with 3. All of these have more, so I really only need 3. On this number, because I'm rounding in the tenths place, it's smaller than the tens place. If you're rounding in the ones place, you won't get into trouble. If you're rounding in tenths or hundreds or thousands, you won't. It's the tens place and the hundreds and the thousands and the 10,000s. That's where people get into trouble with silly rounding or bad rounding. So here I'm looking at the 7, and I'm only going to look at the next digit, which is 9, to see if I round the 7 up to an 8, and I do. So 29.8 grams of C8H18. Any questions? Okay, mass-to-mass conversions again. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to the reaction. Okay, that's all very nice and interesting, and but all these words up here, we didn't need them at all, actually. This is our important part. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? We have our balanced chemical equation. And I'm going to take this number from in among all these words, and I'm going to write it under this formula in the equation. I have 5.50 grams of that, and they want to know how much HCl in grams. So here's HCl. So that's what they're asking me about, and they want grams. These guys are also in the reaction. The question doesn't ask me about them. I do not need to use them in any form. So again, our path is going to be grams to moles to moles to grams. We're starting with grams of magnesium hydroxide. And we go to moles of magnesium hydroxide. And then we're going to go to moles of HCl, because that's what they're asking us about, and then to grams of HCl. So I'm going to start with 5.50 grams of magnesium hydroxide. And I'm going to have 3 conversion factors. And so grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl to grams of HCl. Once you write that path down, that tells you what to put in the numerator of all these fractions. And then I take the previous unit and bring it down. I take this unit and I bring it down here. I take this unit and I bring it down here. So this is going to be grams of MgOH2. And those will cancel out. And here's going to be moles of MgOH2. And down here, moles of HCl. Any questions? Now I need numbers. I like to do the one in the middle first because it's the easiest. I need how many moles of HCl? Well, I go up to the equation. It says 2. 2 moles of HCl. And I need to know how many moles of magnesium hydroxide? 1. We didn't write the 1 here. If you don't write a 1 there, that's okay. Because if you divide by 1 or don't divide by 1, it doesn't change anything. But if you want to write the 1 there, by all means do it. Now this first term and this last term, those are molar masses. Molar masses are always the mass of 1 mole of the substance. So I'm going to have to calculate these. So magnesium hydroxide. So I've got 1 magnesium, 24.31. Where'd you go? Yeah, 24.31. And how many oxygens are in that formula? 2. 2 times 16. And how many hydrogens? 2. 1008. So then I do the math on that. 24.31 plus 2 times 16 plus 2 times 1.008 equals 58.326 grams per mole. 1 mole of it weighs 58.326 grams. So I've got 1 mole, 52.58.326 grams. And then I need the molar mass for HCl. That's a little easier. I've got 1 hydrogen, 1.008, and 1 chlorine. And so that's going to give me 36.458 grams per mole for the HCl. Gram is in the numerator, so that's where the number goes. 36.458 per mole. Any questions? So 5.5, you just go straight across. Times the top, divide by the bottom. I'm going to divide by 58.326. I'm going to multiply by 2, divide by 1 if you like, times 36.458 divided by 1. And I come up with 6.8758. And I realized, oh, I actually only need 3, so I could stop writing now. Here I'm rounding in the hundredths place. That's not a dangerous place to round. Tens, hundreds, thousands, those are the dangerous places to round. So I'm keeping the 7. I'm getting rid of the 5. This is 5 or greater, so I need to round the 7 up to an 8. And so this is 6.88 grams of HCl. Because 6.8758 is closer to 6.88 than it is to 6.87. Any questions? And another example. You can't say there aren't enough examples. And the sheer number of examples here should give you some indication of the importance of this type of calculation. This is like super important. One component of acid rain is sulfuric acid, which forms when SO2, a pollutant, reacts with oxygen and rainwater according to the following reaction. Assuming that there's more than enough oxygen in water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the third kilograms of SO2? So we threw a little bit of a little tiny wrench into this one with using kilograms instead of grams. Okay, SO2. So we have to select the writing tool first. That's what we have to do. 2.6 times 10 to the third kilograms. And they want to know how much sulfuric acid in kilograms. There are different ways to do this. I'm going to show you one that's maybe a little longer, but less confusing. So what have we normally been doing? Grams to moles to moles to grams. Well, let's go ahead and figure that out. So that would be grams of SO2 to moles of SO2 to moles of what? Where's the question mark? H2SO4 to grams of H2SO4. But we have kilograms. Can we convert grams to kilograms? Yeah. So we could take grams of H2SO4 and just add a step on here and convert to kilograms of SO4, H2SO4. But we also had to start with kilograms, and so we could start with kilograms of SO2 and convert to grams of SO2. You okay with that? Seems like a mean trick, doesn't it? So this time we're going to have more fractions. It'll be okay. We may have to write smaller. 2.6 times 10 to the third kilograms. What goes on the top of the next fraction? Grams of SO2, and then moles of SO2, and then moles of H2SO4, and then grams of H2SO4, and then kilograms of H2SO4. And we're following this same pattern down here. Oh, that should have been SO2. Down here, we're going to have kilograms of SO2 because we want those units to cancel out. And we're going to have grams of SO2, so those units cancel out. And moles of SO2, so the units cancel out. And moles of H2SO4, so the units cancel out. And grams of H2SO4, so the units cancel out. You guys doing okay? So the easy one is the mole to mole in the middle. H2SO4 has a coefficient of 2 in front of it, so I'm going to write 2. And SO2 also has a coefficient of 2. I'm going to write 2 in front of the SO2. Then I need a molar mass for SO2. I'm going to do those at the top. So for SO2, I've got the mass of sulfur, 32.07, plus 2 times the mass of oxygen, 32.07 plus 2 times 16, 64.07. Grams per mole. So that's for the SO2. So 64.07. No, that's the wrong place to write it. I zoomed in too far. 64.07 grams of SO2 to moles of SO2. And then I need sulfuric acid, H2SO4. So that's 2 times the mass of hydrogen plus the mass of sulfur plus 4 times the mass of oxygen. .086. grams per mole. So that's going to go in here, because this is where I have grams of H2SO4 to moles of H2SO4. So I put it with the grams. That part is the same as the previous couple of examples. Grams to moles to moles to grams. Now we have to deal with the kilograms. What does kilo mean? 10 to the third. So over here, I have kilo in the bottom and I have nothing in the top. A gram does not equal a kilogram. So I need to put something in the top that is equal to 10 to the third. That is equal to kilo, which is 10 to the third. 1 times 10 to the third grams is equal to 1 kilogram. And then over here, at the other end, now I've got kilo on the top, and I've got grams in the bottom. Is 1 kilogram is equal to 1 times 10 to the third grams. Now, some of you may see that that conversion cancels itself out. That's cool. If you don't see that, we've got it all written down. We're just going to punch it all through the calculator, and we'll all come up with the same correct answer. So 2.6, and then on your calculator, use that EE button. And as you press the EE button, say times 10 to the, and then the 3. You don't need anything else in there. Times, and then this one you're going to enter as 1 EE3. I'm going to divide by 64.07. I'm going to multiply by 2 and divide by 2, and multiply by 98.086, and divide by 1 EE3, and press the equal sign. 3980.39 and some other stuff. Kilograms of H2SO4. Did you get 3980 point stuff? If you didn't, you're having an issue with your calculator, and you need to talk to me so that we can straighten out your calculator. It's your calculator's fault. How many significant figures should this answer have? 2. Is that a dangerous place to round? Yeah, it is. That's the hundreds place. I'm rounding 3,980 to the nearest hundred. That's not 40. It has to be close to 3,900. So let's put this in scientific notation and then round it. 1, 2, 3. I'm moving the decimal point 3 places. So this is going to be 3.98039 and all that other junk times 10 to the third kilograms. And I want to keep 2 significant figures. I'm going to look at the 8. The 8 tells me I need to round the 9 up. 9 rounds up to 10. What does that do to the 3? It goes to 4. So this is 4.0 times 10 to the third kilograms of H2SO4. If we rounded it without putting it in scientific notation, we'd end up with 4,000. But we'd have a hard time indicating that the first 0 is a significant figure and the other 2 aren't. Any questions?